AC TIG welding. AC is the preferred method for welding aluminum and magnesium with the TIG welding process. AC is alternating current, so it's both a combination of positive and negative currents. Okay, aluminum and magnesium are both similar metals. They're non-ferrous. They look alike. They're lightweight, strong, and they unfortunately propose a couple of difficulties when you weld them, which we'll get into here in a minute. I also want to point out that in my picture here I have one cycle. So in the US we use 60 hertz. Okay, so 60 Hz or 60 cycles. So between these we have one full cycle, which is 120 direction changes, or this would be 1/120th of a second, and this would be 1/60th of a second. What about aluminum and magnesium? What's the issue? What's the big deal? Well, a lot of people really enjoy welding both of them. They're actually really just amazing to look at when you get skilled and you look at the beads and everything. But both aluminum and magnesium alloys are lightweight, high-strength, commercially available metals. Both materials have corrosion resistance, good electrical and thermal conductivity, which sometimes, the thermal conductivity can make it difficult to weld these when they're thin because they want to warp on you pretty easily. Their physical properties are similar in that they are shiny and silvery, and then both pose the same difficulties as they have extremely strong oxidation layer. Okay, so I drew a piece of metal here, and that metal will actually melt the aluminum itself around 1200 degrees Fahrenheit, but this little guy here, this little layer, is going to melt about 3 times that, so maybe around 3600 degrees Fahrenheit, and it's this microscopic layer. And the reason that happens is actually looking at the chemistry of these two elements. Okay, so we look at a periodic table of elements and we see magnesium is 12, so it has 12 electrons. Well, we have the first shell, which can have 1, 2 electrons. It's full. That's all that it'll take. The next one can have 8, so we have 8 electrons in the second shell. Now that takes us up to 10, so we have 2 electrons left that can go in this last shell. And so in that last shell we have 6 spots available, and that's where the issue comes in, where we want to get these oxygen elements or atoms will want to fill that last shell, and they create this extremely tight bond. Same thing happens over here. You have all this space available in that outer shell, and that's what makes it difficult. So there's a whole bunch of steps that we could take to properly prep our metal, and we're going to go through that next. So number one, we want to actually make sure if we have clean metal we can use, great. If it's metal that's out in the field, it's been in service, maybe it's less than clean, that's fine. If we can wipe it clean, you can use some type of acetone wipes. They're totally available out there. Go to your welding shop and pick them up. Or you can just buy a can of acetone. Remember, this stuff can be a little dangerous, so use gloves and take the proper precaution. Wire brush to break up the oxide layer. So we recommend you use a stainless steel bristled brush that is only used on aluminum. Do not cross-contaminate. Aluminum is extremely soft, and if you wire brush with aluminum and then you go to steel, or you're wire brushing slag, the slag will get stuck onto the bristles, and then you're just going to embed it right into that soft aluminum. So get an aluminum brush that you only use on aluminum. That'll help break up that oxide layer prior to welding. Electrode selection: zirconiated, seriated, lanthanated, and the blended types. I believe we call them the lasers. The lanthanum, yttrium, zirconium blend are great for AC. Any of those are great. I would avoid any type of thoriated. There are different thoriated rods. Probably the most common that most people know about is the red rod. That's why I put this in red. That's 2%. But there is a 1%, there's a 4%. that are out there. Avoid thorium. They're not meant for AC welding. And then back in the day, everybody used the green pure electrodes. And yes, they will work maybe on your transformer rectifiers, but inverters, they actually encourage you to use some type of oxide blend. Basically, the tungsten's blended with an oxide, and they will definitely outperform your pure tungsten. Yeah, you'll see that these are cheaper, but again, you get what you pay for. Last thing, filler rod selection. Match the base metal and filler rod to the desired properties that are required for the job. So chances are you're going to see one of two rods. Okay, you got ER 4043, which is aluminum and silicon, and then you have ER 5356, which is magnesium and aluminum blend. Okay, you'll notice the 4043 is a lot softer than your 5356, but you can take a look at one of the charts and pick the proper filler rod. Okay, those are easily found in a textbook or on. All right, so getting back into this whole AC, what does it really mean to us? So we have AC, we're going to have positive side, negative side, and the positive side is actually going to be your cleaning action. So when you think about direct current electrode positive, the electrons flow from a negative to a positive terminal. Okay, so if the electrode is positive, that means your base metal is negative, meaning that the electrons are going to flow base metal. Here's your base metal. Here's your tungsten rod. They're going to flow upwards that way. Okay. Then we have our negative side, which is the opposite, straight polarity, and your electrons here are going to flow from the electrode down to the base metal. The negative side, that little bit of negative side, so we're basically split half and half, is what actually allows that tungsten to kind of survive. So when those electrons jump this way, it's allowing this rod to cool from the shielding gas. And when it's the opposite and the electrons are flowing upward, it's putting an intense amount of heat on that filler rod and starting to break it down. That's why really these machines will only allow you to do a certain percentage of positive. Okay. Again, we're looking at 60 cycles per second, and that can be changed depending on the machine. So let's take a look at what I wrote here on the side. Positive cleaning action through what we call cathodic etching. You'll see the etching on the outside of the bead. It could be wide or thin depending on how much cleaning action you actually have, but it looks like just kind of like a white crust, and that is basically telling you that the electrons are blasting through the oxidation layer and removing it. Okay. Electrons move from the base metal to the electrode and blast through it, cleaning or removing it. Some machines can operate at around 60% or slightly more positive, but not much more, as a tungsten would overheat, as I said. So, maybe some of these new inverters can hit like 70% positive, but probably a transformer rectifier is going to be around 55-60%. Okay? Negative, that's your penetration. So you got the electrons going down. So the heat's not on the rod, the heat is on the base metal, and that's where you get your penetration. Okay? So about 2/3 of the heat is on that base metal. And these machines can run transformer rectifier inverter probably up to about 99% negative. So you can have almost all of it negative, and just 1% of that is a cleaning action. And obviously we would use something like that on thicker metals. All right, so our more advanced machines can jump into different waveforms, but the original AC waveform looks like this. This is your sine wave. You take a trig class, they're going to have you draw some sine waves and explain how it all works. If you know about sine, cosine, tangent, this is where it comes from. Here's your sine wave. Okay, that is not a desired welding process on AC. Maybe back in the day those were the original, and for the longest time now they have actually had this conventional square wave. The conventional square wave, even though the machine may say square wave technology, it's not perfectly square. It's still rounded. I suppose. So, you know, you got to think your amperage. So this would be 0, no arc. Now you are arcing, and it's immediate. You're here, okay? Rather than this is like, okay, I'm low, I'm getting higher, getting higher. Here's my peak. This is really where I'm getting the good cleaning action on the positive side, the great penetration here on the negative side. This is like immediate. It's straight up, boom, you're here, you're spending time, you're getting up there to your peak, and you spend a little bit more time close to peak, and then it's like instantaneous, it flips. So which is a good thing, because then we don't have to worry about your arc going out in between. Really, there is a continuous high frequency going on in the background to keep that ignited, because technically every time you run into that switch on, especially AC there, it's going out. But since this line's straight up and down, it's instantaneous. Okay, so that's a conventional square wave that you would see on a transformer rectifier machine. Now we're getting into inverters down here with these two. Okay, so you have a true square wave. Again, they instantaneously switch positive to negative, but you're actually spending time at that peak current, which is where you want to be. So you're truly getting, you know, 100 amps at positive, 100 amps at negative, where you actually want to be. And then some of these more advanced ones will give you this triangular. So you're only just barely peaking out there, here and here, and that's your triangular waveform. So I can tell you that some of these newer machines can actually get into all four of these. I see. They call this your old soft sine wave. You get your conventional square wave, a true square wave, and then your triangular wave. Sometimes it's not the easiest to get into these modes. You actually have to go into the interface of the machine, but it is all out there. And the cool thing about these machines is that you can really save just about any setting you want. So if you're welding really thin, aluminum or magnesium, or really thick, you can decide which AC waveform you want, and go from there. AC balance. Okay, so these machines, transformer rectifiers, and inverters will allow you to adjust your balance. Okay, so let's say we are looking at this is square wave, and we're going to just spend a little bit of time on cleaning action and a lot of time on penetration. Well, that probably means that we are welding metal that is thicker. We're looking for more heat, for more penetration. We're not so worried about the cleaning action. Okay, here we have a different story. We have a lot more cleaning action and less penetration. So maybe because the metal is thinner, we don't want to have too much penetration, or maybe the metal is less than clean. It's got a really thick oxide layer, so we want to spend some more time on the cleaning action side. So that's AC balance. That's on any machine out there that is a TIG machine for AC. There is also auto balance on some machines, but we're not going to discuss that now. But it is out there. Usually there's a little green light that is like amplitude. Amplitude is how much amperage or current I have on each side of our zero mark here. So there's no arc. We got zero current. So here, maybe we want 100 amps on cleaning and 50 amps on penetration. So if you see something like this, it's going to give you a wider bead, larger etching, because we're doing more cleaning, more heat on the cleaning side, and then we're going to get a lot less penetration. Okay, here we have the opposite. This is less cleaning action, so maybe like 50 amps here and 100 amps here. So we're going to get a narrow weld, thinner etching zone, but we're going to get more penetration. Again, this is an inverter only option. AC frequency, inverter only. Example, a machine could maybe change the frequency from 20 to 200 hertz. It could be more than that. I'm sure the more we move forward with technology, we're going to see that these machines are going to be just doing absolutely crazy things. When people are messing with your frequency, you can hear it. This is extremely high pitched, and this is a much lower sound, much lower pitch in sound. But what I did is I put our standard 60 hertz, so you're using a transformer rectifier. We do have pulse. That's not the same as changing our frequency. Pulsing is like pulsing your heat high, low, high, low, high, low. This is just the AC. How many waveforms are we going to have? Okay, so 60 hertz standards, and then I just drew what I'm saying is 40 hertz. Okay, so you can see it's a little bit longer time spent on each side than our 60. And then we have 200 hertz where, you know, we're doing 20,000 hertz per second, okay, or cycles. So again, two different styles of welding. There are some benefits to using each of these. All right, and finally, electrode prep. So I wanted to discuss electrode prep. You know, when we're welding DC negative on almost all of our TIG welding projects, you know, steel, stainless, and a lot of the different alloys, you take the unground electrode and we basically cut a point into it. Okay, and as long as you don't contaminate, it stays pretty sharp. Better quality rods will stay sharper longer, and all that good stuff. But it's a little bit different with AC. Remember, we have our positive side, which is going to be our cleaning action, but that's going to equal a ton of heat. Those electrons are jumping to the electrode, creating just a tense amount of heat on it, and it's going to make it want to melt. Okay, so what I'm going to show here is a couple different things. This is on ground. That's fine. Start welding with it. It works perfect on ground. Who cares? Fresh out of the box, toss it in there, start welding with it. You'll be okay. Especially on a transformer rectifier. If you have a lot of positive, it's going to ball up like this. Or some people put it on positive, they ball it up, and then they put it on AC and weld with it. Don't actually have a ball on the end. That's a terrible idea. Your electrons are going to jump off out here. They kind of come out like this and down, and you're going to create a wider bead just by that alone. If you really had these the same distance off, same amperage, all the variables are the same, you would see somewhat of a difference. So don't use it like that. We'll say no to this. Okay. Let's continue on. Here is rounded. So if it just comes down and it's rounded like this, that's great. That's what we're looking for. Transformer rectifiers all day long, no problem. I've even gotten away with transformer rectifiers. I've been able to sharpen it and really just get a little bit ball at the end. I use a lot more negative, and I'm still welding on some pretty thin stuff and able to do that. Just don't overheat it, and it's fine. And which that leads to this last one, which is the tapered ball. Easier to maintain that on a regular inverter when you change your amplitude. So if you have less current on the positive side, you'll have less heating here, and you could sharpen it, and only the tip will actually ball on you. And it may even look smaller than that. So it's impressive. Things worth mentioning though, you know, I did brown because zirconiated is a great AC rod. So I did brown for all these. But, you know, if this is happening here, then maybe you need to step up the size of your electrode. So if you're using a 16th inch and you're welding some pretty beefy aluminum, you need to go to 332 or 1/8 inch, something bigger that can handle the amount of heat from those electrons on that positive side. So something else to consider, okay? That wraps up all the AC welding. Just, you know, some basics that you should know when you're going to prep and weld and set up for AC. Hope that helps.